Today we're going to talk about electric potential energy. So when I have two charges close together, they will either attract or repel each other, which tells me that there must be some sort of potential energy between the two. And I think the best way to understand electric potential energy is by analogy. So we can, suppose we look at this picture here. Here's a person throwing a ball up, and the ball is going to come up and then come down, largely due to the force of gravity. So the force of gravity is pulling down with a magnitude of the mass times the gravitational acceleration g. And we know that as the ball reaches different heights, it gets different amounts of potential energy. The gravitational potential energy for this ball is just going to be given by the mass times g times h. Similarly, what we can do is we can make an almost exactly the same picture, except do the same thing with charge now. So suppose you were standing on a plate that's negatively charged, and you throw a ball up, but rather than just being a ball, it's a ball that has some positive charge. Well, we know that the positive charge is going to feel a force from the negative charges on the bottom, and that force is going to be equal to the charge times the electric field, in the same way that the gravitational force is equal to the mass times the gravitational field, or equivalently, the gravitational acceleration. So if we, by analogy, construct the electric potential energy, so this would be our electric potential energy, UE, well, all we did is we took the force mg and multiplied by the distance away from the Earth. Here, we're just going to take the force QE and multiply by the distance away from the negatively charged plate. So we can have gravitational potential energy, and in the exact same way, we can also have electric potential energy. So we have that our electric potential energy for a charge Q is going to be equal to the electric field that that charge experiences times the distance d in which it has moved, the distance d it has moved in that electric field. So to see how that works, we're going to build up a little data table here. And we're going to look at a slightly different situation from the one I showed you before. Here, we're going to consider two parallel plates that are charged, which I can get by just taking two parallel plates and connecting them by a battery. So we have here an electric field of 4 newtons per coulomb between the plates, drawn in orange, and the plates are separated by a distance of 1 meter. So what I want to do is I want to compute the electric potential energy at different distances between those two plates. So I'm just going to measure, I'm going to put a charge here, and I'm going to measure the distance d to that charge. And we're going to do this for a bunch of different distances. We'll do it for 0 meters, 0.25 meters, 0.5 meters, 0.75 meters, and then all the way to the top, let's say 1.0 meters. And I'm going to make this charge, let's make it a 1 coulomb charge. So it's a 1 coulomb charge. We're going to be measuring the electric potential energy for that 1 coulomb charge. Well, let's see, that would mean Q is 1, E is 4. So I just have to take 1 times 4, so that's, that'd be 4 newtons, times whatever the distance is. So if I put my charge all the way at the bottom here, that would be 0 joules of potential energy. Much in the same way that if I have an object on the ground, we'd normally say it has 0 joules of gravitational potential energy. And if I move it up to a height, let's draw our different heights in here. If I move it up to a height of 0.25, that would give you 1 joule of energy. And if I move it up to a height of 1/2 of a meter, that would give me 2 joules of energy. Over here, 3/4 of the way up, that would be 3 joules of energy. And if I go all the way up to the top, that would be 4 joules of potential energy. Now let's suppose that instead of having a 1 coulomb charge, so this was for Q is 1 coulomb. Now let's do the same thing, but for a new charge, that's twice as big. So that'll be 2 coulombs. And again, we're going to compute the potential energy. I'll call this potential energy prime, call that Q prime. And as before, if my 2 coulomb charge is at the bottom, I'm going to have 0 joules of energy. But now, if I bring it up to a height of 0.25, I have twice as much charge. So we're going to get twice as much energy. That's going to be 2 joules of energy. And it's going to be the same factor of 2 bigger, because it's always going to be the same 2 coulombs of charge. It's twice as big as the amount of charge we had in the first case. So we're always going to get twice as much energy. So this will be 4 joules, this will be 6 joules, this will be 8 joules. So we have these 2 different cases, but in both cases, the situation is pretty much the same. The only thing that's changed is the charge itself. So we would like to have some way of representing the potential energy per unit charge. We've defined our electric potential energy, and we saw that the electric potential energy is proportional to the amount of charge that you have. So if I put more charge between my parallel plates, that charge would have more electrical potential energy. If I double the amount of charge, I'm going to get double the electric potential energy. If I triple it, I'm going to get triple the electric potential energy. But we'd like to define some quantity that doesn't depend on how much charge there is, so we can represent a bunch of different situations for a bunch of different charges. Physicists have done that, but they did it in kind of a screwy way. So, as I said, we want the electric potential energy per unit charge. So they defined something that does this, that is equal to this quantity. However, they gave it kind of a screwy name. They gave it the name electric potential. Now, as you can imagine, that's going to cause some confusion because electric potential is related to electric potential energy. But electric potential is not the same thing as electric potential energy. Fortunately, electric potential also has another name that I'll try to stick to, and that is called voltage. We'll say that the voltage or electric potential is equal to the electric potential energy per unit charge. I should emphasize that the potential or voltage is the same potential and voltage that you see rating batteries. So it's the same voltage that we dealt with when looking at current and Ohm's law last term. It's the same potential that you have across a battery difference. So the electric potential difference, if you have a 9-volt battery, the electric potential difference between the positive end and the negative end is going to be 9 volts. So that's all that potential means, but we also have this other definition in addition to what we normally think of when we think of batteries. It's also associated with the amount of potential energy that charges in the circuit are going to have, the difference in potential energy that they're going to have going from the positive end to the negative end of the battery. So we've defined the electric potential to be the potential energy you get per unit charge. And you get a different amount of potential energy at different points in space. So for example, if I connect a 4-volt battery to this, in fact I'll get exactly this situation that I have here, where if I look anywhere at the negative end, we could define that to be 0 volts. And if I look anywhere at the positive end, everything up here is 4 volts. Similarly, if I look in the middle, everything on that line is going to be 2 volts. Everything on this line will be 3 volts. Everything down here will be 1 volt. Since I have a uniform electric field, the voltage just changes in nice even steps. Now that will not always be the case. This is only the case that it changes in nice even steps when we are dealing with uniform electric fields, as we do when we have a parallel plate system that's charged up. So I want to go over just a few different properties of voltage and how voltage interacts with charges. The first thing I will note is that positive charges accelerate down in voltage. That's fairly easy to see. If I put a positive charge up here at 4 volts, it's going to be repelled and pushed towards lower voltage. This is also why electric current in a battery flows from the positive end of the battery to the negative end. Positive charges accelerate down in voltage. Similarly, negative charges accelerate up in voltage. So if I were to put a negative charge in here, let's say I put the negative charge at 2 volts, it would be attracted to the positive charge. It would accelerate upward in voltage. Other things I will note. So we have a word for each of the green lines that I've drawn here. Each of those green lines have the same electric potential. Here's the 4 volt line, here's the 3 volt line, here's the 2 volt line. Because they all have the same, everywhere on the line has the same potential, we call these equipotential lines. And it must be true that equipotential lines it must be true that equipotential lines are perpendicular to the electric field. So we can imagine that the electric field, it's kind of like an arrow that's pointing to in the direction that the potential decreases. So these are our equipotential lines. The electric field, as we can see at all these different points, it's going to be perpendicular. And this is generally true. Not just for this geometry, but for any geometry, the equipotential lines are going to be perpendicular to the electric field. Again, the electric field points in the direction that the potential is decreasing. One more point about potential, or voltage if you prefer. I just want to emphasize this. The potential is different everywhere throughout throughout space. So we could say that every point in space has some potential. Right now my body has some electrical potential. That being the case, since electric potential changes throughout space, potential is also a type of field. It's a field in the same way that the electric field is a field, and the gravitational field is a field, and the magnetic field is a field. Every point in space has some value of electrical potential. electric potential, I should say. And for that reason, we can describe it mathematically as a type of field that extends throughout space, where each point in space has some value, some voltage associated with it. So far, we've talked about the electric potential and electric potential energy in situations where we had uniform electric fields. But that's not always the case. Sometimes we have electric fields that are non-uniform. A very common example of that is dealing with point charges. So for a point charge, I have an electric field that comes out in all directions. And we'll take some value. And we want to be able to draw the equipotential lines for a situation like this. To do that, we can recall the rules for potential lines, one of which said that the equipotential lines had to be perpendicular to the electric field lines. So I can draw a series of equipotential lines just by making them perpendicular to the electric field lines. So let's say, let's suppose that I told you that this was the 100 volt line, and maybe this we'll say this one's the 100 volt line. We'll call this one, give myself a little bit more writing room here, we'll call this one the 200 volt line. Maybe this is the 50 volt line. Each concentric sphere around that charge tells me the potential at that point. Whether it be 50 volts, 100 volts, 200 volts, whatever it happens to be. So how do I actually compute what that potential is for that point charge? Well, one thing that helps is if I know what the potential energy is. And there's a very simple formula for the potential energy between two charges. It's K, the electric constant we've written down before, Q1, Q2, divided by R, where R is the distance between the two charges. So if I've got two charges, there's a distance R between them. I can tell you how much potential energy there is associated with that configuration. I'm going to put a box around this, and I will note that this is the potential energy between, actually I'll say four, 2-point charges. Well, the electric potential, or voltage, is the potential energy per unit charge. So what will that look like for point charges? Going back to my original picture over here. Well, that would mean that my potential is going to be K, the charge, we'll call it Q1, divided by the distance away from the charge. So this would be the voltage or potential a distance away, a distance r away from a point charge. I want to update our mantra for, try it again. I want to update our mantra for dealing with electric fields, forces, and charges. So before, we had said that charges create fields. specifically electric fields. Now I want to say charges create not only electric fields, but also voltage and potential. So charges create the electric fields, then the electric fields create forces. But the charge not only creates an electric field, it also creates this voltage and potential. So charges create voltage and potential, and that voltage and potential tells you what the energy associated with those charges is. So charges create fields and voltage or potential. The fields create the forces, the voltage and potential tell you what the energy associated with those charges is.